Jerry QU, as all of you should know, and today I'm going to tell you a story. The story is about me back when I was in grade 7 or grade 8, and I just first started learning HTML code. You can see HTML code over here. I was super excited that a couple of symbols and a couple of characters typed into my old, overheated, and broken computer could create something seen by millions on the internet. We hear about people like Mark Zuckerberg, who created a billion-dollar company with something that I now have in my pocket. It's amazing. But that was done several years ago. And today, the technology that's pushing the forefront of what machines can do is machine learning. Now, all of us have heard about machine learning before. It's that thing that makes self-driving cars drive. It's that thing that lets you search up your friends' photos by just typing their name into Google Photos. It's that thing that's said to revolutionize every industry that there is. And we all know that there are many different categories within machine learning. There's supervised learning, there's unsupervised learning. But what I focused on over the past couple of weeks is reinforcement learning. You may wonder why I have a picture of a dog up here, if you can see it. And that's for two reasons. One, because when you search up reinforcement learning on Google Photos, you get this, a bunch of math, and it's not the best splash page, which kind of attests to how new machine learning and reinforcement learning is. But also because a dog and basically every living thing is actually a good representation of how reinforcement learning actually works. Let's take into consideration a situation. Imagine you want to train a dog to sit when you tell it to sit. What do you do? Anyone want to raise up their hand? What do you do? How do you train a dog to sit? Yeah.
Well, like when it sits, you give it like a treat.
Yes, you give it a treat. You give it a reward. You give a dog a treat when it sits. So you tell the dog to sit, it has no idea what to do. So maybe it just runs around or it jumps up and down. And eventually it'll sit. And when it does sit, you give it a treat. And over time, as you do this over and over again, the dog gets reinforced and he starts to learn that when you tell it to sit and he sits, he will get a treat. That is the essence of how reinforcement learning works. And if you don't understand anything after this point, this is all you have to know. Since I'm going to go into a bit more depth for people who want to learn how to actually implement this and how this works in computers, but essentially this is how it works. And in every reinforcement learning model, you have these 4 key things. You have the agent, in this case the dog. You have the state or you have the state that it's in this case it's in a yard, maybe it's jumping up and down. You also have actions, so maybe it can jump, it can run around, it can sit. And you have rewards, in this case a treat. And these are the 4 things in every reinforcement learning model. So now we're going to go a bit in depth into how reinforcement learning works in terms of math. So if you're scared, don't worry. You already learned the intuition behind how reinforcement learning works. So imagine that you have this agent, a robot, in the bottom left corner right there, and you want it to move up to this top right corner up here. Let's say that when it moves to that square there, you give it a reward of +1. Instead of using real life tangible things like a treat, we're using numbers because this is math. We're representing this on a computer. So how does the agent or this robot down here decide which way to move? Well, it has 2 possible options. It can move up or it can move right. But it has no prior knowledge, so it's just going to make random decisions. So let's say it just moves right, and moves right again, and moves left. And then over time, maybe after 10 other random steps, it finally gets up to this square up here at the top right, and it gets a reward of +1. It feels really good, in a sense, if you're thinking of emotions. But how does it learn the series of steps that led him up to that point? Well, what we use is something known as the Bellman equation. And this equation here, basically you set the value at a state. So for example, we set the value at this state here at x = 1 and y = 2. We set that value of that state to a number that represents the rating of that state, how good that state is. So, how good is this state compared to this state, compared to this state, compared to this state? Of course, this state is better than this state since it's closer to the objective where you're getting a reward of +1. And you set that equal to the reward of taking action A in state S to maximize your reward, plus the value of the next state multiplied by a discount factor, which is represented by gamma. If you have no idea what I just said, don't worry. Basically, with that formula, you get this thing. You get these values here. V = 0.66, V = 0.73, and so on and so forth. And now your reinforcement learning algorithm, if it starts down here in the bottom left corner, it can just look around it, see where the highest value is, and go there. So of course it's going to go up, up, right, right, and finally it'll get to the objective. And that is how a reinforcement learning algorithm learns. Now, this is still abstracting things a little bit here, because if we think of the real world, we don't have a finite number of states, or we don't have a 3x4 grid of the number of states you can be in. In real life, there's so many different factors. You can take into consideration the pressure around you, you can take into consideration your values, your beliefs, you can take into consideration where you are on the planet Earth. And there are so many different factors that can be taken into account. And there's so many different possible states that you can't set a value for each possible state. So instead, what you do is you train a neural network to approximate the value at the next state given your current state. And you have no idea what I just said, we're gonna look into it. This is called deep Q learning. And just to mention something to begin with, in deep Q learning you have these things called Q values, which is essentially the same thing as what I've been calling so far as a value. It's the rating at a certain state, so how good a state is. So the Q value at this stage here is 1, the Q value there is 0.9, the Q value there is 0.81, and so on and so forth. And so what you do is you take a deep neural network, you put in as input your current state. So let's imagine that your current state is over here at v equals 0, or actually imagine it's here at v equals 0.73. And you're going to take as output the Q values of all the possible states you can move into. In this case, you're going to have 2 output nodes, one for this state up here and one for this state down here. So the Q values would be 0.81 and 0.66. You then take the maximum of those Q values and you take that action. And that is essential, and that is how deep Q learning works. And you have no idea what I just said. I'm going to use an analogy as well. So the neural network that I just mentioned back here is essentially like your brain. Basically, let's take an example. Imagine you're in a situation or a state. You're playing hide and seek, and you have, let's say, just to simplify things, you have 2 possible actions. You can either run around, or you can actually go and hide. And let's say this is your first time ever playing hide and seek, so you have no prior knowledge. For those of you who know machine learning, it's as if you just initialize your deep neural network, and the weights in your neural network are completely randomized. And so since the weights in your neural network or in your brain are completely randomized, the Q values that are taken out will also be completely randomized. And so the action you take will be completely randomized. And so let's just say, just out of pure chance, the Q value for running around was bigger than actually hiding. And so you decide to just run around in circles. Well, then the outcome of your actions occur. You run around in circles and you get caught first since you're playing hide and seek and you're not supposed to be running around in circles. And you feel really bad because everyone's laughing at you. And basically what you've just gotten is a negative reward. You've gotten feedback from the environment that tells you this was bad. You got a negative reward. And with that negative reward, we can pass it through our Bellman equation and get a negative Q value. With the negative Q value, we can train our neural network and it'll adjust the weights so that the predicted Q value is closer to the actual Q value. So before we thought, oh, if we run around, we're gonna get a really high Q value. It approximated that. It just guessed that in random. But in actuality, we got a really low negative Q value since everyone was laughing at you. And so the weights in the neural network are adjusted to reflect that. And so the next time that you are in the same state again, when you're playing hide and seek, you're gonna calculate these Q values again, and what's gonna happen is the Q value for running around is gonna be lower than the Q value for actually hiding. And so you decide to actually hide. Everyone congratulates you because you win, and you got a high reward, which translates into a positive Q value. And then the weights inside your neural network are adjusted so that the predicted Q value is closer to the actual Q value. And essentially what's happening is your brain's reinforcing that you should do this action in this current state. And that is what's happening in reinforcement learning in a semi-intuitive sense. And so now I'm going to show you a video of a deep Q network that I created that drives a virtual self-driving car between 2 points, if it works. All right. So essentially what's happening here is I have this virtual car, which is represented by this little thing here, and it's learning to drive between the top left corner and the bottom right corner and keep on going back and forth. It's getting I believe a +10 reward when it gets to each corner, and it's getting a -1 reward for every time step it takes. So it really, or less, a -0.1 reward for every time step it takes. And so it really wants to get to these corners here. Now, also I'm drawing sand, as you can see here. And this sand, basically, if the car runs into it, then it's going to get a negative reward, a reward of -10. So it's really de-incentivized to run into these walls. So it's going to learn to go around them over time. It's going through them right now, but it'll learn over time to go around them. And the cool thing, I'm just gonna talk over this video about reinforcement learning is that you can do something like this with it. If you were to implement a supervised learning algorithm to do something like this, it would be impossible because you have to label all of your data points. At all of these time steps, you have to say, you should have done this, you should have done this, you should have done this. But you can't do that since there's so many time steps. And so what deep reinforcement learning lets you do is abstract that level of labeling your data. Instead, you just give it feedback from the environment. You tell it, you give it a reward if it did something good or if it did something bad. And over time, it learns what actions it should take, which is something really cool about reinforcement learning. Yeah. It's going back and forth, you can see that.
Yeah, stop.
All right. And this technology here, of course, it can be applied to so much. So like deep reinforcement learning is being applied to algorithmic trading on the stock market, which is something you can't do with normal supervised learning because you can't label all your data points. But what you can do is take the amount of money that you gained or lost and feed that back to your model to tell it if it did good or if it did bad. So it kind of abstracts that level of labeling your data. It's also being used to make game bots for different games out there and also for self-driving cars. All right. Okay, now before what I was explaining to you was a deep Q network. But there are a lot of different models in reinforcement learning as well. You have the A3C model, which stands for Asynchronous Advantage Actor Critic. And this model, I'm not going to go into detail here, but essentially, it runs a lot faster than DQN, especially when you don't have GPUs, which I don't. So this is actually a really good model for me, and this is what I've been looking into over the past week or two. Also, I've been looking into distributional reinforcement learning, which is a different way of doing reinforcement learning. Instead of approximating a single Q value, you approximate a distribution of probabilities of different Q values. And it's best explained if I show an example. And I was hoping this would be up there, but since it's over here, it's really, really small. But basically, this has a deep Q network, and it's approximating a distribution of Q values. It's saying that there's a 50% chance that the next Q value will be 0, and there's a 50% chance, around 50% chance, that the next Q value will be 10. Now, if you only outputted one Q value, then it would average those two, and it would output a Q value of 5. But the actual probability of getting a Q value of 5 is almost 0. So this doesn't properly represent the data. So instead we generate a distribution of probability of Q values. And this has been shown to almost double the speed of training a reinforcement learning algorithm, at least on Atari games. And this is pretty new. So I think it was released a couple of months ago. And so it's only been tested on Atari games. Yeah, and those are the two things that I've been kind of looking into these are the things I've been looking into over the past couple of weeks. And these are the two things that I want to implement in the near future, the A3C algorithm and distributional reinforcement learning. And to just end off, I really want to kind of stress the significance of reinforcement learning. I talked about it a little bit before, but reinforcement learning, I think of it at least as like kind of the next step in machine learning. You started off with if-then statement rules where programmers would have to program all that, and then you abstracted that to machine learning where you put in an input and an expected output, and it slowly learns over time how to generate that output. And then you have reinforcement learning where you don't have to label your data. You don't have to give an expected output. All you give it is a response from the environment it's in, and normally that response is already defined in the environment with like games and self-driving cars or in the stock market, and it abstracts another level of labeling. It automates the step of labeling, which is a huge step in machine learning right now. Thank you.